Hello, my name's Michael Lee. This is an online pre-recorded talk for the Society for Mathematical Psychology 2020 meeting. The topic of the talk is model-based wisdom of the crowd for sequential decisions. The wisdom of the crowd is the idea that aggregating the behavior or decisions of individuals can lead to an aggregate or crowd decision that is in some way well performed. This is usually applied to simple decisions and by taking simple statistical measures like means and medians and modes, such as aggregating the estimates that a number of people make about the number of jelly beans in a jar by taking the mean or the median, or by finding the majority or the mode of the decisions of a set of people on a multiple choice question. There are some problems, however, for which aggregating the knowledge of individuals might be useful, but don't take the form of individual decisions. For example, you might poll a set of people on what sequence of rides they would recommend that you do on a day trip to Disneyland, or you might ask a set of fantasy football experts what sequence of players they would suggest you draft for your team. For these sorts of sequential decision problems, a simple statistical approach like taking the mode is unlikely to work well because there are so many possibilities. For example, you might ask 100 friends what sequence of rides they would recommend at Disneyland, but no two friends provide exactly the same sequence, and so there is no mode that you can take. In this talk, we're going to consider the way in which cognitive models can help provide useful wisdom of the crowd aggregation for sequential decision problems like these. There has been just a little work on this theme in the past with combinatorial optimization problems, but we're going to extend it to three classic sequential decision problems, and this is a good time to introduce my co-authors. We're going to look at the balloon analog risk task with Jeff Kuhn, we're going to look at optimal stopping problems with Bobby Thomas, and we're going to look at bandit problems with Holly Westphal. The balloon analog risk task, or the BART, is a widely used measure of risk propensity. On each problem, a decision maker here is faced with a series of trials where they can either pump up a balloon to increase its value or bank the value they already have. Pumping the balloon further inflates it and risks the balloon bursting, at which case you lose all of the value. So the wisdom of the crowd question here is, can you combine the pumping and banking decisions across individuals to balance out the risk propensity and lead to good group behavior? Here's a first behavioral wisdom of the crowd analysis based upon 56 subjects doing 50 problems in each of two bursting conditions. The yellow distributions show the mean reward, the mean amount of money earned by the subjects in each of the two conditions, and the black line shows the average of their reward. The red is the optimal you can do, and the optimal is slightly funny here because the problems that were chosen in this experiment weren't quite representative of the bursting environments. But the important point is the green dot shows what happens if you aggregate the behavior of the individuals in terms of the pump and bank decisions and take the modal behavior. And we can see in both conditions it doesn't perform especially well. The reason the behavioral mode doesn't work well is illustrated by this example problem. This is a case in which the balloon burst on trial 13, individual behavior is shown below and the aggregate behavior is shown above. You can see that on trial 7 the bank decisions outweigh the pump decisions, and so that's what the group does. But notice that the crowd is being progressively based upon only those people continuing to pump the balloon. The others have been eliminated from the crowd because they banked earlier, and so the crowd is progressively being conditioned upon riskier and riskier subsets of the individuals. As a model-based approach, we used a simple two-parameter model of the BART proposed by Van Ravensway and colleagues that estimates a risk propensity and behavioral consistency for each participant. What that model lets us do is keep including everybody in the crowd by using the model to make predictions about what everybody would have said at every stage. The results of that sort of behavioral aggregation over the predicted decisions are shown by the blue squares in this diagram, and you can see that these are much better performed. The other thing we can do with these models of people's individual BART behavior is apply the wisdom of the crowd to brand new problems for which nobody has actually provided observed behavior. Instead, we use their prediction based upon the model of what they would have said if they'd done this problem and take the aggregate over those predicted decisions as the crowd behavior. So here you can see some results for the same two environments. The yellow shows what the individuals would have received in terms of mean reward again. The red is now optimal and truly optimal because this is enough problems to be representative, and the blue shows how the wisdom of the crowd based upon model-based predicted decisions performs, which is very well in both environments. Let's turn now to optimal stopping problems. In the full information optimal stopping problems we consider, people are presented with a series of values and simply have to choose the maximum. The catch is that they can't return to earlier values in the sequence, so you have to choose it at the time it's presented, which creates uncertainty. We consider data from the same Guan 2019 studies that had 56 people do 40 optimal stopping problems in each of 4 conditions. Those conditions varied the length of the sequences and the distributions from which the values were drawn. The behavioral wisdom of the crowd approach here is simply to work your way through the sequence and, as the crowd, take the first value that the majority of individuals chose. You can see the performance here for each of the 4 conditions. This performs relatively well. It's up around optimal and among the best performing individuals in 3 out of the 4 conditions. Despite this good performance, we still considered a model-based approach so that we could generalize to new problems. We considered a series of threshold models that have been proposed in the literature, including people having a fixed threshold above which they choose values, or having their thresholds linearly decrease, or be fixed for some period before they start to decrease towards the end of the sequence. Here are the thresholds that we inferred for all of the individuals in each of the 4 conditions, and the solid black line shows the optimal thresholds. You can see there are large individual differences, but that in general people are kind of centered in variability around the optimal thresholds. When we use the decisions that we predict individual people would have made based upon these threshold models, we get very similar wisdom of the crowd answers as we did for the behavioral aggregation that we looked at earlier. More interestingly and perhaps impressively, however, when we apply the models of individual behavior to brand new problems for which no person provided behavioral data, the predicted decisions still lead to a crowd aggregate that performs almost optimally in all but one of the conditions. The third and final problem we looked at are bandit problems. We looked at 2 choice bandit problems in which people have to choose repeatedly between 2 slot machines, each of which has some fixed but unknown rate of giving reward. People have a fixed number of trials where they choose between these 2 alternatives, and so the goal is to explore early to find which machine provides the reward and then exploit that machine as you get towards the end of the total number of choices that you're allowed to make. The behavioral data we used involved 4 different bandit problem conditions. It's a summary here of how individuals performed in terms of the proportion of total possible reward they achieved in each of those 4 conditions. Most tellingly, the behavioral wisdom of the crowd approach, which aggregates individual behavior by taking the modal decision of all individuals who are in the same bandit problem state as the crowd currently faces, is shown by green and performs extremely poorly. This poor behavior surprised us, so we had a fairly detailed look at what was causing it. The basic problem is shown by this example analysis. So if, for example, on the very first decision the crowd does not receive a reward, so there's a single fail for the left and nothing on the right alternative, it turns out 713 times when people were faced with that decision, they continued to choose the left one that had already failed. This isn't actually the optimal thing to do. It leads to a lower expected reward, and the 713 people who chose it were less well performed than the 339 people who chose the right thing. That's shown here by the average reward that those players received, 4.54 versus 4.75. And so the consequence is the crowd exploits. If, for example, that failed again, that's shown immediately below. Now you've got 2 failures on the left and none on the right, but the majority of people in that situation continued to exploit the one on the left, 337 versus 141, and those people again were a subset of people less well performed than the people choosing the right alternative, and this is a general pattern that repeated for all conditions and for many, many game states. The problem is that you progressively condition your crowd or sub-select your crowd for people who are over-exploiting, and the majority behavior leads you deeper into this problem where the crowd is now fully exploited one situation and has only got behavior to aggregate over people who also sub-optimally found themselves in those situations. So you get this kind of descent to the bottom that leads to extremely poor crowd behavior in this particular type of problem. Because it seemed like the model-based approach had a lot to offer for bandit problems, we were more expansive in the set of models we considered. We considered 5 different theoretical models: win-stay, lose-shift, an extended version that allowed for win-stay probabilities being different from lose-shift probabilities, a tau switch model that explicitly moves from an exploration state to an exploitation state, and two famous reinforcement learning models, epsilon greedy and epsilon decreasing. We also considered three different contaminant models. You can see here that most participants, but not all, were inferred to use the extended win-stay-lose shift. Some of the other substantive models, there was also evidence that some participants were using those. There was very little evidence of contaminant behavior. Bandit problems are a bit unlike BART problems and optimal stopping problems in that there isn't one specific sequence that defines a problem that we can look at, and this is because of the stochastic nature of the reward. So really what we're limited to in the Bandit problem case is to apply the model-based approach to new problems, and you can see those results here. It performs extremely well. It basically provides crowd behavior that is extremely close to optimal in all four of the conditions. And the intuition for this good performance is exactly the intuition for what the problem was in taking the behavioral wisdom of the crowd for Bandit problems, which is now that we've got models that says what everybody would have said in the crowd for every state of every game, the model is able to make a prediction about what people would do in these counterfactual situations. The model-based crowd is now conditioned upon all of the expertise, not sub-conditioned upon a set of over-exploiting participants. So now we've explored the behavioral wisdom of the crowd and a model-based wisdom of the crowd in three different sequential decision problems, and for ones in which we know what optimal behavior looks like, which provides a good way to benchmark. In one of those problems, optimal stopping, we saw that the behavioral wisdom of the crowd worked well, and the model-based crowd still had the advantage of allowing generalization to new problems for which people hadn't provided behavioral data. But in two of the problems, we saw that standard behavioral wisdom of the crowd can lead to dysfunctional crowd behavior. In BART problems, it tends to aggregate upon people who have higher risk propensity as you work your way through the problem. And in Bandit problems, as we just saw, it tends to condition upon people who overexploit. And so, as I hope we've shown, the model-based approach can address this weakness by basing crowd behavior upon what every individual would have done, not just those who find themselves in a particular situation in a sequential decision problem, and it also has that advantage of generalizing to new problems. So the hope would be that you could apply this approach for something other than sequential decision problems that are already well characterized and have optimal behavior, like the ones we mentioned at the beginning. The idea would be that you would build a cognitive model of what preference your friends would have for different Disneyland rides conditioned upon having visited these rides so far in a day, so that you could use all of their wisdom at every stage in planning out a day trip. Or similarly, for the fantasy football experts, you would build a model of who they would draft next given the state of the board, including players who maybe they originally hoped to draft but are no longer available, so that you can use everybody's wisdom at every juncture in the sequential decision-making process. Thank you for listening to this presentation. I look forward to getting your feedback and questions as part of the online conference format. There's a project page on the Open Science Framework listed here that provides code and data and additional results. As always, I'd like to thank the sponsors of the lab and thank all of the members of the lab posing in the Conquest of the Planet of the Apes movie poster perspective here, and especially Jeff and Bobby and Holly, the three co-authors with the yellow arrows pointing towards them. Thank you very much.